Hello, and welcome to another overview of AbLead, our antibody analysis and engineering suite. Today I'm going to show you the incorporation of solvent exposures into an analysis for engineering. So let's take a look at this set of antibodies. These are potentially lead antibodies. You may want to engineer some of them. And as we scroll along, we can see that there are various issues and attributes. For example, one of the things that might require solvent exposure evaluation is a tryptophan oxidation potential for degradation of activity. And some of these antibodies have some pretty severe tryptophan oxidations. This one, for example, this one has 4, but this one has 2. That a little easier to evaluate in an example like this. So let's just choose this one, and I'll come in and look at the liabilities. I'll go to the analysis menu and select liabilities. There are a lot of different liabilities in this molecule, the stability violations being one of them. If I move this up to 5, it lowers the number of stability violations. But in this case, for the purposes of this demo, I'm just going to show the tryptophan oxidations. So there are 2 of them. They're both in the heavy chain, one in CDR1 and one in CDR3 by North definition. And if I click up here on its entry, since I have a PDB file loaded for this molecule, I can evaluate those tryptophan positions. And if I look at this and look just at those violations, I may say, yeah, those both look exposed. I think that they might oxidize. And it's the pyrrole ring here at the beginning of the tryptophan that's the issue. This one might be a little more buried, so I'm not sure about that. But this one looks fully exposed. So it's beneficial to get some more detail. Well, how do you get that detail? I've added a solvent exposure tool that allows us to evaluate both at the residue level and at the atom level those positions. So if I toggle back over to liabilities, we'll look at this first one. It's heavy chain, IMGT position 39. So we'll come over here and you can get attributes of the molecule. This is the FV surface area calculated in the presence of whatever was in the PDB file. The full surface area of the FV, the ABHAN class summations, the per residue summations, and a color-coded entry of solvent exposures for every residue in the PDB file. So this PDB file had the first constant domain, and that's helpful because any residue that's in the FV that would be included by the constant domain would be artificially exposed if this wasn't included in the PDB file. So I like to calculate structures of fabs at least. Now, if we mouse over, you can see it shows the solvent accessible surface area, the side chain accessible surface area, and the relative accessible surface area. And that relative value is relative to an extended version of that amino acid with glycines on either side. So it gives you an idea of the percentage that's shown. For example, here only 30% of the possible residue is shown. Here 66% is shown, and so on. Now, if we come over and look at that tryptophan of interest, it's tryptophan 39, and I'm only showing in the liabilities tryptophans in the CDRs. So if I click on that, it scrolls down to center on that tryptophan. And you can see here that it's barely exposed, 9.7. But what about the atoms in the pyrrole ring? So if we click on this toggle, it opens up the atoms in the pyrrole ring. You can see the backbone's not exposed at all. And here's that CD1 next to any1. And these atoms are what's going to be oxidized. Here we're looking for oxidation. 2.4 is barely exposed. I generally consider 10 square angstroms to be about the interaction of one water molecule. So this is barely exposed. It's possible that this could oxidize, but maybe not. I'm not so worried about it. But as you remember from the liabilities, it was 114 that looks more exposed. So let's look at the pyrrole ring of 114. So back over to the solvents. Solvent exposure evaluation, we'll find 114, it's right here. And we'll click on that, or we could just scroll down, but I like to get the mouse over. It's just a quick view of how exposed that is. It looks like it's exposed. All of the exposure is in the side chain, as you can see. Let's open up the atoms here and take a look at CD1. It's not exposed at all. The exposure is out in the benzene ring, and that's not as much of an issue, not as much of a concern. So these two tryptophans are likely of low risk. I'd still come into a structure evaluation tool. I prefer to use the molecular operating environment from the chemical computing group for things like this. But even as a quick view, I can toggle this into full screen and then just look at space fill. And there's that tryptophan. And you can look and see that indeed that pyrrole ring is mostly buried. There's probably not much range for flexibility of this loop. It doesn't stick up out of the core FV. This heavy chain is actually quite short, so it limits the amount of flexibility that this tryptophan could have. So low risk for oxidation and degradation of this tryptophan. I'm going to leave full screen and I'm just going to toggle this off and back on again. That'll force the system to show it back as the liability view. And I wanted to show you that indeed this short heavy chain CDR3 is fairly inflexible because it's mostly in a sheet conformation. So you just have the loop here that would allow some flexibility. However, this loop could be rearranged. This is just a model. So the assumption of oxidation and degradation on these tryptophans is an assumption, but it's one of those that are made during engineering as to whether or not these should be modified. I will say it's very difficult to modify tryptophans directly in an antigen interface such as this, but that is a demo of utilizing the solvent exposure tool along with liabilities to help with decisions about lead selection and engineering of an antibody. I hope you enjoyed this overview and look forward to hearing from you.